and I'm just going to go straight to that and give me the answer, which is in seconds for the full 3 sig fig. Is it 1.40? Okay, 1.40 seconds. Okay, happy with that? So it's a very typical thing. You might not be asked to get this, but if you get the acceleration nice and easily from forces, you can get omega straight off, and that allows you to work out things later on, if you know, amplitudes and things like that with other formulas and velocities.
The forces in direction together.
Yeah.
That means it's the force towards so it doesn't matter the acceleration.
Yeah, you are right. Okay. That's, when I was your age, I couldn't get around because we all know that acceleration's got to be acting towards there because it's negative. Yeah. However, you also think about the graph of a velocity time graph, and as you are looking to see how. Well, first of all, if you start with speed, displacement time graph, you're looking at any kind of line. As time moves on, time is always moving that direction. This will always have a positive gradient to it like that, and therefore you've got dx by dt. Okay, that will be that's because you've shown the effect of that with the rate of the change of x with respect to time, and the same again for acceleration is you're seeing x has got to be increasing. Same thing here, it's got to be increasing, and when you differentiate it again with respect to time, it's got to make sure that x is increasing. Okay. That's why we say it always goes in the direction of x increasing. Okay, it's hard to get your head around. I hope that makes sense. X increasing.
It says in the question that the force is always towards O.
Yeah, and intuitively you'd say that the acceleration is towards there, and then you're and then it won't all work out. It's all to do with that differentiating with respect to time. Time's always moving, yeah, and x will therefore, if you are moving, x will be moving positively. So, yeah.
So,
yeah.
So these questions, it's not actually doing the full circle, it's just going backwards and forwards.
Well, yeah, if you're looking down on a bird's eye, what you'll see is the carriage will do this, and what you'll see is that carriage is doing this.
Okay.
So you're looking down on top of the circle, if you will.
So it's just going backwards and forwards.
Yes.
Modelling it.
Using the circle. Okay. All right. Next one comes from that, and scroll down. Let's make sure we got that right. I left it as that. There it is. So print screen, which is that, and go to what do I need to go to? Back to there, and go to a fresh page. Edit and paste, and I suppose I can zoom in and get rid of all this. Okay, right, zoom in, right, scroll up, and scroll back down, and it says, this is example 9, is it? 9? Yeah, 9. It says, a particle is moving in a straight line with SHM, okay, full stop. Its maximum acceleration is 12 meters per second squared. Its maximum acceleration is 12 meters per second squared, and its maximum speed is 4 meters per second. Full stop. Okay. Calculate A, the period of the motion, and B, the amplitude of the motion. Right. So what's the max acceleration? The max acceleration is x dot dot. Well, the acceleration formula is x dot dot minus omega squared x. Do you agree? And the maximum acceleration is when x equals a. Now, the acceleration they've given you is just the acceleration. There's no direction to it. It's the magnitude they're giving. So the magnitude of this is negating the minus. Do you understand that? So therefore, x dot dot is equal to omega squared x. It's just the magnitude. Bang, and bang. So therefore I can say that 12 is equal to omega squared A. And I'll come back to that in a second, because we're going to use the second bit now, which says the maximum speed. And the formula we're going to use is x dot is equal to omega A. Okay, and we know that this is equal to 4. So 4 is equal to omega A. Okay, divide one by the other. And you've got, therefore, omega is equal to 3. It is 3, isn't it? 12 divided by 4. 3. And it's rads per second. Okay, omega is 3 rads per second. Right, and therefore I can shove it back into here, and therefore A is equal to 4/3. That's it, 4/3. And what's the units of that? Standard index units. What's amplitude? Meters. What is the amplitude? It's measured from O to the extremity. Yeah? Right, so we've got that now, and it's going to help us to work out part A, which now says the period of the motion will tau is equal to 2 pi over omega, which is 2 pi over, and omega is 3. And it's seconds. Okay? You know, I don't know what that will be in thingies. I would write it down, I suppose. Is it 3 sig fig? Anybody? 2.09 seconds. Okay? Right, and then part B, it simply says the amplitude of the motion. Oh, we've already done that, haven't we? The amplitude of the motion. So it is 4/3, 1.33 metres. So 1.33 metres. Okay, so we can go back to the notes now. Everyone happy with that? Right, desktop, scroll down, click onto that, and back to normal. You alright, Brads? Yeah, okay. Over page, and example 10. A small rowing boat is floating on the surface of a sea, tied to a pier. The boat moves in up and down in a vertical line, and it can be modelled as a particle moving with simple harmonic motion. The boat takes 2 seconds to travel directly from its highest point, which is 3 metres below the pier top, to its lowest point. So what is 2 seconds? It is what of its period? Half. Okay, so I can get straight from here. Do you understand that? I'll do a drawing anyway. Here's the pier. Okay, you always need to do a drawing it, and we've got here is 3 metres going down from there, from the pier top, 3m. We're going to have some kind of centre we're going to put here, and then further down here is the lowest point. Okay. Right, and it takes 2 seconds from here, so half period is 2 seconds. Therefore, tau, which is equal to 2 pi over omega, is equal to 4. So, straight off, omega is equal to pi by 2. Okay, rads per second. Right. And then it says, the boat takes 2 seconds to travel from the highest point, which is 3 metres below, to the lowest point. The maximum speed we're given again, so we're told that x dot max is equal to 3. So straight off we can get x dot is equal to, what was it again for max speed? Omega A. And I've got 3 is equal to pi by 2 A, and A is therefore 6 over pi. And what's the units for that? Meters. Okay, so what was the question? Amplitude. Well, we've got the amplitude of the motion now. So that's part A, really, all of that. Okay, now the time taken for the boat to rise from its lowest point, which is down here, to a point 5 metres below the pier. Okay, right, I want to work out what this actually is. Can someone tell me what that is? Amplitude 1.91 metres. So I know that this distance here is 1.91 metres, and this distance here is 1.91 metres. Now it says the time taken for the boat to rise from its lowest point to 5 metres below. So lowest point, 5 metres below. So I need to come from down here, do you agree? And 2 metres is going to knock me into here. Okay, that there is 5 metres below. So I'm below this centre, what's that? Centre of oscillation, okay, equilibrium. Okay, so that's 5 metres. So I want to know, what is x? Is x going to be measured from here, from here, from here? Where's x going to be measured from? What do they always tell you x is measured from? The centre of oscillation. So do you agree x is this distance here? Okay, x. I'm going to highlight it, it's really important you understand this concept. So how do we get that? Well, it's simply going to be, well, this distance here is, from here to here is what? Well, from there to there is just 2, yeah? So 2 take away, that's going to give us, 2 take away, that's going to give us what we want, isn't it? So this bit here is 2 minus, and I'm going to keep it in the unrounded answer. I don't like rounded answers, so I understand what I'm doing now, and I know where it's going to fall, so it's take away 6 over pi. Okay? X, I put x is equal to that. X is equal to that. Metres. Everyone happy with that? So B, right, it says from its lowest point. So which one do I use if I'm starting at lowest point? So I'm going to put down here start. If I'm starting at lowest point, which one, cos or sin? Cos. If you think of that circle, the cos starts at the extremity. So we're going to use x equals a cos omega t. Okay? What does x equal? Well, that's always measured. Is it positive or negative if I'm starting here? Positive. If I was starting there, would it be positive or negative? Negative, because it's 0 there, negative's gone beyond. Okay? Right, so it's on the same side I want, so x is. So x is 2 minus 6 over pi. We know a is equal to 6 over pi, and we know omega is equal to pi over 2. And we're after the time it takes, time taken to get to there, to rise to there. So here we go, just shove it all in. 2 minus 6 over pi is equal to a, which is 6 over pi, cos omega t, which is pi t over 2. Right, take that, and what is it? It's going to be 2 minus 12 over pi, isn't it? And arc cos it. Are we all? Oh, okay. We end up with t is equal to arc cos of 2 minus 12 over pi, and I've got to times it by 2 and divide by pi. And we're only after the first time it does it, because you think cos is an oscillating graph, but this is the first time it happens. The second time will be over here, but it'll be negative. Right, but anyway, okay, and it'll be, when it comes down that full circle, it'll be in the 4th quadrant when it hits there again. Right, what's it going to be, that there? Have I done something wrong? You've got to be in radians.
Yeah, it wouldn't make a difference.
Help me out, what have I done wrong? Hold on a second, I agree with you.
A, you've put in the P.
Yeah, A's right, so if you times 2 by pi, you get 2.
Oh, it wasn't A plus, sorry. Yeah, my mistake, I can see it, yeah. Schoolboy error. So this bit here is wrong, isn't it? It is, yeah, I don't know what I did there. It's times by it, isn't it? Yep. So it is 2 minus 6 over pi, and it is times by, is it pi over 6? Yeah. Pi over 6. Right, that's it, sorry. So t is equal to 0.97, 3 sig fig. 70 seconds. Okay. Well, let's check we've got the answer right. 9.0, yeah, okay. Right. It just looks like there's another example. Okay, everyone happy? Got that down? Paying attention, Dave, because this is where he's going to lose it otherwise. You won't be teaching this yourself, it's going to be quite awkward. Okay, this is the last example, thank God. Right, a particle P is moving with simple harmonic motion along a straight line.